Okay, so for the first one here, it's a third root. And remember what that means when we're reducing it is we can take out sets of three. Three factors that are alike can be taken out. So if we factor 2,592, I'm going to take a step up here and I'm going to do that. Well, when I look at this, it's really tough to figure out what it can be divided by. But I can see right away that it can be divided by 2, so let's divide it by 2. That would give us 1,296 left over. It's still even, so I can divide it by 2 again, so let's do that. That leaves us 648. Still divisible by 2. Let's keep doing that. 324, still divisible by 2. That would leave us with 162. Well, it's still divisible by 2. That would leave us with 81. That's not divisible by 2 anymore, but what can it be divided by? 9. So we get 9 and 9. That 9 splits into 3 and 3. That 9 also splits into 3 and 3. So that tells us in this 2,592 is 5 2s, or 2 to the 5th power, times 4 3s, or 3 to the 4th power. Then we've got x to the 13th, y to the 20th. And you recall, doing that root is basically dividing the powers by the index of that root and doing a division and a remainder. 3 goes into 5 how many times? Once. So 2 to the power of 1, or just 2, is going to go on the outside. How much would be left over? What would be the remainder? 2. So 2 to the power of 2 stays inside the radical. Let's look at the 3. It's 3 to the 4th power. So that 4th power gets divided by a root index of 3. 4 divided by 3 is 1. So that's 3 to the power of 1. What's the remainder? 1. So 3 to the power of 1 stays inside the radical as well. X to the 13. What is 13 divided by 3? 4. So x to the 4th comes outside the radical. How much is left over? 1. So x to the 1 stays inside. For y to the 20th, we take the power of 20 divided by 3, which is 6. And what's the remainder? 2. Good. So what we have here, 2 to the 1st times 3 to the 1st, well, that's just 2 times 3, which is 6. X to the 4th, y to the 6th, times the cubed root. Inside I've got 2 squared, which is 4, times 3 is 12. X to the 4th is just x. X to the 1st is just x, and y squared. So that is 6x to the 4th, y to the 6th, times the cubed root of 12xy squared. Any questions on that? So factoring really is the key to simplifying that calculation of reducing a radical. And remember, it's just whatever that index of the radical is, you're taking that much out of the power for each one we bring out. We're dividing the power by the index of the radical, index of the root. For number 2 here, we remember that separate, in a fraction, if we have a separate radical on the numerator and the denominator, as long as the index of that radical, index of that root is the same, in this case both are 5, we can combine those into a single fraction. So we can make this the 5th root of 64x to the 18th, y to the 4th, over 2x to the third y to the negative 6th. And now we can divide that out inside the radical first. What is 64 divided by 2? Perfect. 64 divided by 2 is 32. X to the 18th divided by x to the third. 18 minus 3 is 15. So that is x to the 15th. And y to the fourth divided by y to the 6th. 4, or negative 6, I should say. 4 minus a negative 6 is 10. Y to the 10th. And the same thing. If we factored 32, we would get that that is 2 to the power of 5. Or 5 2's multiplied together. So 5 divided by 5 is just 1. That's 2 to the power of 1. X to the 15th. 15 divided by 5 is 3 with no remainder. Y to the 10th. 10 divided by 5 is 2 with no remainder. So that is simply 2x to the third y squared. Any questions? Okay, as you did the homework in my math lab yesterday for what you got to, did you have any questions on any of those that you'd like me to go over? Okay, like I said, I realize this is a little bit more difficult homework. I'll try to make sure, being the holiday weekend, I'm not sure how often I will get to my email, but I will try to check my email at least sometime on Saturday. So if you have any questions, just use that Ask My Instructor button on your homework, and it should send me a copy, and I'll try to answer it. At some point on Saturday, I'll try to answer questions. Okay, so these radicals. Before we launch into operations with radicals, let's take a look at some applications that they're used for. One thing that they get used for, if you look at a right triangle, if I have two of the sides of that right triangle, I can always find the third side. Now the two shorter sides, the two sides that make the right angle, notice they make the L of the triangle, are called legs. The third side that's always opposite of the right angle, or the longest side of the triangle, is called the hypotenuse. And we're used to labeling the legs sides A and B, and the hypotenuse sides C. Of course, you all know A squared plus B squared equals C squared, our Pythagorean theorem. And we use those radicals to solve this, because it becomes 8 squared plus 15 squared equals C squared. And of course, you square the 8 to get 64, the 15 to get 225. You combine the 64 and 225 to get 289 equals C squared. Now we have to solve it. We have to get C by itself by square rooting it. And of course, we know that when you square root something, technically that's 17 or negative 17. Negative 17 doesn't make any sense, though, because it's a triangle. You can't have a side of a negative distance. So 17 is going to be that answer. Often, when we use computer programming or just punching this in the calculator, rather than writing it out in long form like this, we adjust that formula a little bit to make it what we call homogeneous. It's a single variable equals everything else, and we don't have to do anything back to that variable. So rather than doing C squared equals A squared plus B squared, we often do the square root to get C equals the square root of A squared plus B squared, like that. In that form, we apply this to our graphs. if I had a point here at 1, 4, and another point over here at, let's call it 13, 9, and I wanted to find the length of the segment or the distance between those 2 points, I would use that formula. It's called the distance formula. And in the distance formula, we create basically a right triangle. And as we look at it, we realize this side here of that right triangle is just the rise from our slope formula. And this side up here of our right triangle is just the run from our slope formula. So the run, remember, was x2 minus x1. That's going to be side A. We'll square it. Plus side B is going to be the rise. That's y2 minus y1. And we square it. So if I ask you to find the distance between the point -8, 11, and, what do I want to do here? -1 and -13. I would apply this formula. That distance is equal to the square root of x2. I can label the points any order I want to. I'll call this 1 and 2. So x2 would be what? -1. It's the 0.2 x coordinate. -1 minus, what would x1 be? Perfect. 0.1 x coordinate is -8. So that's going to be added to, what's y1 or y2 going to be? -13. Good. 0.2 y coordinate minus y1 of 11. And that's squared. With it in this form, of course, we can just punch it in the calculator now if we want to. I'm going to go ahead and work it out by hand. -1 minus a -8. Remember, that comes plus a +8, so that would be 7 squared plus -13 minus 11. -24, good. 7 squared is 49. 24 squared is 576. We add those together. We get 625. The square root of that is 25. Those points are 25 units apart. I'm going to have you guys do a quick example. So find the distance between these 2 points. I'm going to give you a minute or so to work that. So this will be the square root of what's going to go in this first set of parentheses? Well, what are the 2 numbers that go in there? -5 minus 3. Good. In the second set? 8 minus -7. Good. if you punch that in the calculator, it does all work out. This is going to end up being negative 8 squared plus 15 squared, and that works out to be 17. So just an actual use of numbers within those radicals. Let's dive back into the symbols and radicals. Let's look at operations with these radicals. So first of all, these radicals can be combined to make numbers in many different forms. And we can have it as simply, the square root of 7, but we could also have, 5 times the square root of 7, where we have a whole number in front of that radical multiplying it. But we can combine it in other ways as well. We might have 3 plus 7 times the square root of 2, where we have a part of it that is a rational number, and then another part of it that's irrational. Remember we said any root that doesn't come out exact is what we call irrational. There's 2 ways to define irrational. One is irrational, is it cannot be expressed as a fraction. Or the other way to think about it is it's a non-terminating, non-repeating decimal. So if you calculate it out as a decimal, it never ends and it never repeats in a pattern. And of course, it doesn't have to be square roots like we have here. We're going to do a lot of work with square roots because they're the simpler ones to work with, but it can be other roots. We might have, 9 minus 3 times the 5th root of 8. That is an irrational number, a radical expression. We can mix several roots into one. We might have 2 times the 3rd root of 10 plus 5 times the 4th root of 3. Those are all radical expressions, and each index of a radical has to be kept different. Not only each index, but each object, the object within the radical. If it's different, it creates a different digit, a different name for that digit. So to combine radicals with addition and subtraction. If you go all the way back to that first day where we talked about whole numbers and addition and subtraction, remember, to combine numbers with addition and subtraction, they must have the same name. For radicals, what that means is has to have the same index of the root and the same object in that root. 5 times the square root of 3 and 7 times the square root of 3 both have the same name because both of them, it's a square root and it's a 3 inside the radical. 8 times the 5th root of 2 and negative 3 times the 5th root of 2. Those have the same name. Both are 5th roots and it's a 2 inside the radical. Both things have to be the same to be able to combine them with addition and subtraction. And then, once we know they have the same name, we combine counts and keep the same name. So let's go back up here. Let's say this is 5 square roots of 3 plus 7 times the square root of 3. The counts would be the 5 and the 7. If we combine them, 5 plus 7 is 12. That's combining the counts. and we keep the same name. The name is square root of 3. Notice that's just like having 5x plus 7x makes 12x. Or this other one, let's say this is addition also. 8 fifth roots of 2 plus negative 3 fifth roots of 2. We combine the counts. 8 and negative 3 make 5. Fifth root of 2, we keep that same name. That's 5 times the fifth root of 2, or 5 fifth roots of 2. If I wanted to combine this or simplify this, it's kind of a mess. We'll start in the left here. Is there anything I combine with the 8 times the square root of 2? Can I combine it with this? No, why not? Yeah, it's a third root, not a square root. Can't do it. How about this one? No. It's a square root, but it's of 3, not of 2. This one? Nope, that's still a third root. How about this one? Yes. So 8 and negative 4 combine to make positive 4. We keep the same name, square root of 2. This one, is there anything we can combine it with? Yeah, that's the third root of 2. We have another third root of 2 over here. So negative 5 and positive 8 make positive 3. We combine those, and we keep the same name, the third root of 2. And of course, nothing to combine with 11 times the square root of 3. I'm going to have you guys try one. Combine that one quick and see what you come up with. So 7 fifth roots of 4 can combine with what? Negative 8. To give us negative 1 fifth root of 4, or just negative fifth root of 4. I can have the 1 there, but I don't have to, right? And then, of course, we combine those to get negative 4 third root of 4. There we go. Sometimes there's reducing that we can do before we combine. We might have a problem like this. 12 times the fourth root of 32 minus 3 times the fourth root of 512. If I look at those, I say, well, they're both fourth roots, but there's a different object in the root. But they can be reduced. If I factor 32, it becomes 2 to the power of 5. There's 5 times 5 times 5 times 5 times 5. What can I reduce that to? Well, how many 2's can I pull out of here? 1. So I pull out a 2. What's left inside that fourth root? Yeah, 2 to the 1 or just 2, right? So what that has become, I pulled out the 2. So that's 12 times 2 is 24 times the fourth root of 2. So the 12 times the fourth root of 32 becomes 24 times the fourth root of 2. Well, that's minus 3 times 512 is 2 to the power 9. I have the fourth root of 2 to the power of 9. Remember, when we simplify, we divide the power by the index of the root. How many times does 4 go into 9? 2. So that's 2 to the power of 2 times the fourth root. What's left inside there? 2 to the 1, right? 9 divided by 4 is 2 with 1 left over. Are there any questions on doing this, taking this fourth root of 2 to the 9th and breaking it into 2 squared times the fourth root of 2 to the first? Okay. So 3 times 2 squared is 4 times 3 is 12 times the fourth root of 2. Now, of course, we see that these are the same name. They're both fourth roots, and they have an object of 2. So 24 minus 12 is 12 fourth roots of 2. Does that make sense? So we might have 7 times the square root of 48 plus 11 times the square root of 75 minus 3 times the square root of 27. In your notes, I want you to combine and reduce those for me. So 28 plus 55 is what? 83 minus 9 is 74. Square roots of 3. Any questions?
Yeah, the last part, the negative 3 square root of 27, I went 3 times 3, so I ended up taking a 9 out, so I got 27.
It's a 9 that you take out, but remember, when you take it out, you got to square root it, so you get a 3 outside.
Oh, yeah, okay.
Yeah, you think of 27 as 3 to the third power. 3 divided by 2 is 1 with a remainder of 1. Now, it's not always going to be simple radicals like that. We might have 7 plus 3 square roots of 8. Actually, I'm not going to use 8. That would be a bad number to use. 3 square roots of 10 plus 5 minus 9 square roots of 10. And we would treat this just like we would an algebraic number. We line up the things that have the same name. We're adding here. So this is 3 plus a negative 9 makes negative 6 square roots of 10. And 7 plus 5 is 12. So that's 12 minus 6 square roots of 10. When you throw in negatives in there, or in subtraction, it can be a bit more complicated. We might have 13 minus 4 third roots of 7 minus 9 plus 11 third roots of 7. So once again, we line them up. 13 minus the 4 third roots of 7. 9 goes with the 13. The positive 11 third roots of 7 goes under the other cubed roots of 7. And we remember we're subtracting now. negative 4 minus 11 is negative 15 third roots of 7. 13 minus 9 is 4. That is 4 minus 15 times the cubed root of 7, or the third root of 7. We might run into something like this. So as we try to work with this, we would first want to try to reduce it. What I would do with this piece here is, remember, we can split that into the fourth root of the numerator and the fourth root of the denominator. Why does that help us? Well, because we can take the fourth root of 81, it is just 3. So this is the fourth root of 5y over 3. Might be more helpful to think of it as 1/3 times the fourth root of 5y. Over here, I can split 80 into 2 to the 4th power times 5. Which means I can pull out a 2. It's got a power of 4, and this is a 4th root. So that leaves me with 2 to the 1st. Nothing, inside the 2's are gone. I used them up. So it's 2 times the 4th root of 5y. Any questions on how that 2 to the 4th came out here and became just a 2? Okay, because the 4th root, 4 divided by 4 is 1 with no remainder. So that's 2 to the 1, or just 2. So 1/3 times the 4th root of 5y plus 2 times the 4th root of 5y. That could be considered 2 1/3 times the 4th root of 5y, but we typically don't write it like that. And we would typically make the 2 1/3 an improper fraction. So we would either write it as 7/3 times the 4th root of 5y, or most commonly, we would write it with the radical in the numerator of the fraction, so it would look like this. 7 times the 4th root of 5y over 3. The reason for that is we don't like having radicals in the denominator of a fraction. So even though the radical isn't in the denominator, we tend to convert this to that form where that radical is clearly in the numerator, just to avoid that appearance. In fact, at some point, we're going to look at something called rationalizing a denominator. If I had 7 over the square root of 2, we don't like that. Remember we discussed yesterday a little bit about when they used to have the root tables for the square root of 2 and 3 and 5 and so on. That's why they reduced things down, so they didn't have to have all these tables. Well, imagine if you were to calculate this out. 7 divided by 1.4140, blah, 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 whatever 2 comes out to be on that table, that's a tough, long division by hand. So they do a process called rationalizing a denominator where they get that radical out of the denominator. Well, remember, you can multiply a fraction by the same number, by anything you want to, as long as it's the same number in the numerator as it is in the denominator. So I just multiply by the square root of 2. So on top, that gives me 7 times the square root of 2. On bottom, what's the square root of 2 times the square root of 2? Just 2. So now I'm not dividing by that ugly decimal that's the square root of 2. I'm multiplying by it, which is a lot easier to do. And then I am dividing by 2, which is a lot easier than dividing by that big ugly decimal. Now again, in the modern age with calculators, that's not as necessary of a task as it once was, but we still do it. Okay, so anyway, now let's look at multiplication and division. To multiply, remember, we do not need the same name. What does that mean? Well, that means the square root of 8 and the square root of 18, even though they have different names, I can multiply them. The fifth root of 4, the fifth root of 8, even though they have different names, again, I can still multiply those. And then, of course, when we multiply, we combine counts. And then we also combine names. Now, I didn't put counts on either of these, so I'll come back to examples with counts on them in a little bit. But for the first one here, if I multiply, I'm combining the names. The square root of 8 times the square root of 18, I can combine that to be the square root of 8 times 18. 8 times 18 is 144. I can actually take the square root of 144, which is 12. Down here I can multiply the fifth root of 4 times the fifth root of 8. They do have to be the same root. They do have to have the same index. But when they don't have to have the same object. I can combine the objects. That becomes the fifth root of 4 times 8, which is the fifth root of 32. And that, of course, the fifth root of 32 is just 2. Now, I purposely did both of these examples so they came out to be whole numbers. But they don't always have to work out that way. We might have examples like 7 times the third root of 12 times 3 times the third root. Again, they have to be the same index of the root at least. Oh, let's do 36. That's not going to work. Yeah, it should work. Why not? So anyway, we combine these. We combine the counts. 7 times 3 is 21. Then we also combine the names. The third root of 12 times the third root of 36 is the third root of 12 times 36. 12 times 36 is going to be 432, I believe it is. And now we have to check to see if we can reduce that. If I factor 432, I know I can take a 2 out of it. That leaves us with 216. Another 2 leaves us with 108. Another 2 leaves us with 54. Another 2 leaves us with 27. Take out a 3 leaves us with 9. So a 3 and a 3. So that's 2 to the 4th power and 3 to the 3rd power. So we got the 21 up front. Can I reduce the 2 to the 4th power with the 3rd root? Yeah, this power is bigger than the index of the root, which means I can reduce that. I can take it out. I take the power divided by the index of the root. 4 divided by 3 is 1. So this is going to be 2 to the 1st that I can take out. The remainder is 1. So 2 to the 1st is left in there as well. 4 divided by 3 is 1 with a remainder of 1. How about the 3 to the 3rd? What's the 3rd root of 3 to the 3rd? It's just 3. And nothing would remain in here from the 3. So I now have 21 times 2 is 42. Times 3 is 126. Times the 3rd root of 2. Any questions there? In your notes, I want you to multiply 3 times the square root of 30 times 7 times the square root of 42. Reducing this is the hard part. If I multiply it out, I have 3 times 7. I'm combining the counts. That's 21 again. 30 times 42. Now, rather than multiplying them out, I'm going to do this. 30 factors into 2 times 3 times 5. 42 is 2 times 3 times 7. So if I multiply them together, 2 times 2 is 2 squared. 3 times 3 is 3 squared. 5 and 7. All I did to multiply them together is I just combined all their factors together. So now reducing this is dividing out those factors. So I got the 21. Remember, the square root has an index of 2. So 2 squared, that can come out just to be a 2. 2 divided by 2 is 1 with no remainder. 3 squared, same thing. 2 divided by 2 is 1 with no remainder, so I can bring out a 3. The 5 and the 7 can't come out. 1 doesn't divide by 2, and another 1 doesn't divide by 2. So I combine. 21 times 2 times 3 is, once again, 126. 5 times 7 is 35. So that's 126 times the square root of 35. Any questions there? It's not always going to be single digits like that. We might have 8 plus 5 square roots of 2 times 5 minus 3 square roots of 2. This gets to be a little bit of a complex multiplication. And we are multiplying. And remember, when we multiply, we've got to do every digit times every other digit. So we'll start out with the negative 3 square roots of 2 times the positive 5 square roots of 2. Well, negative 3 times positive 5 is a negative 15. Square root of 2 times the square root of 2 is just 2. Actually, I'm going to write this off to the side. So that's negative 15 times 2, which is going to be just negative 30 here. Next, I take that negative 3 square roots of 2 times the 8. Why combine the counts? Negative 3 times 8 is negative 24. Square roots of 2. So now I've combined the negative 3 square roots of 2 with every digit in that top number. I move over to the 5. I do 5 times 5 square roots of 2. I multiply the counts. 5 times 5 is 25. Nothing to multiply the square root of 2 by. So that's just square root of 2. And now I do the 5 times the 8, which is 40. You'll notice, however, that can combine with the negative 30. So now I combine negative 24 times the square root of 2 and positive 25. Negative 24 and positive 25 makes 1. Square root of 2 or just the square root of 2. Negative 30 and positive 40 make positive 10. So I can either write that as the square root of 2 plus 10 or 10 plus the square root of 2. Either one of those is acceptable. Now, one thing is, it helps if the index on our roots are the same. So if they're not the same, we really can't combine them. There will be examples where there are different indices, but in different terms, and we'll deal with that. I'll show you how to deal with that. Something like this, we're going to go ahead and multiply it out. 3 minus 5 times the cubed root of 4, 7 plus 2 times the cubed root of 18. Notice I don't have the same object in the root, I just have the same index. So I start out 2 times the cubed root of 18 times the negative 5 times the cubed root of 4. I'm going to do it off to the side over here. 2 times negative 5 is negative 10. The cubed root 4 times 18 is 72. Can the cubed root of 72 be reduced at all? Yeah, 72 is 2 to the third power times 3 squared, right? Which means I can take out the 2. So negative 10 times 2 times the third root of 3 squared. So that's a negative 10, or sorry, negative 20. Negative 10 times 2 is negative 20. The third root, 3 squared, is 9. Then I have that 2 times the third root of 18 times 3. 2 times 3 is 6. Third roots of 18. Time to move over to the 7. 7 times negative 5, third roots of 4. Well, 7 times negative 5 is negative 35. It's going to be the third root of 4, though. So again, I have to keep going. That's a positive 6. Negative 35 times the third root of 4. And then I got 7 times 3, which is just 21. You will notice here, there's absolutely nothing that we can combine beyond this. So this here is our answer. 21 minus 35 times the cubed root of 4 plus 6 times the cubed root of 18 minus 20 times the cubed root of 9. That is ugly. I won't argue with you there. Let's have even more fun with it. Let's do something like this. Remember, all that's saying is the square root of x plus 8 minus 6 times the square root of x plus 8 minus 6. So we'll write it out the long way. Negative 6 times negative 6 is a positive 36. Negative 6 times the square root of x plus 8. That's just negative 6 times the square root of x plus 8. Now we have the square root of x plus 8 times negative 6. That's also a negative 6 times the square root of x plus 8. Finally, the square root of x plus 8 times the square root of x plus 8. That's x plus 8. But I'm going to do this. I'm going to write the x here. I'm going to put the plus 8 over here because we can combine that with the 36. So I've got x. I've got negative 6, and negative 6 makes negative 12 times the square root of x plus 8, and plus 44. Any questions on that one? So let's try, now let's step back a half a step and do this. Something like that. We're just distributing here. 2 square roots of 3 times 5 square root is 6. 2 times 5 is 10. Square root of 3 times square root of 6. 3 times 6 is 18. We're going to be able to reduce that. We'll do that in a minute. 2 root 3 times negative 3 root 15. 2 times negative 3 is negative 6. Square root of 3 times square root of 15. 3 times 15 is 45. 18 factors to 2 squared times 3. So we can take out that 2. will give us 20 times the square root of 3. What's that?
B squared times 3 is 18?
Yes. Oh, sorry, I did that backwards. Let me try that again, sorry. 2 times 3 squared. How's that? That better?
Okay.
So I can take out the 3 to get 30 times the square root of 2. Sorry about that. And then, of course, 45 is 3 squared times 5. So I can take out the 3 there to get negative 18 times the square root of 5. That's where that would end up, is 20 times the square root of 2 minus 18 times the square root of 5. Let's try something like this. We've got the square root of 7 minus 3 square roots of 5 times 4 plus 2 square roots of 7. Again, notice we don't need to line up columns here because we're multiplying. We do not need the same names. I start out multiplying these two. I'll do the counts. 2 times negative 3 is negative 6. Square root of 5 times square root of 7. 5 times 7 is 35. So it's negative 6 times the square root of 35. Square root of 35 cannot be reduced. Here, however, 2 square roots of 7 times the square root of 7. 2 times 1 is just 2. Square root of 7 times the square root of 7, however, is 7. So 2 times 7 gives us 14. Four times negative 3 square roots of 5. 4 times negative 3 is negative 12. Square root of 5. Then, of course, 4 times the square root of 7 is just 4 times the square root of 7. The only question now is really what order should we put it in? There's a couple of different rules that none of them are really universal and held to all the time. But I usually put the whole number, the rational part first, the 14. And then I usually go up in order of smallest to largest. So I do minus the 12 root 5 plus the 4 root 7 minus the 6 root 35. But really what order those roots go in, really, there is no hard and fast rule for it. I want you guys to try one in your notes. Seven plus 6 times the square root of 5 times 7 minus 6 times the square root of 5. This actually looks a lot like our sum and difference products, and it actually is a sum and difference product. We've got the negative 6 square roots of 5 times positive 6 square roots of 5. Negative 6 times positive 6 is negative 36. Square root of 5 times the square root of 5 is just 5. Negative 36 times 5 is negative 180. Negative 6 square roots of 5 times 7. Negative 6 times 7 is negative 42 square roots of 5. Move over to the 7. 7 times 6 square roots of 5 is a positive 42 square root of 5. And then 7 times 7 is 49. And we notice negative 42 square root of 5 and positive 42 square root of 5 cancel out. We've got 49 minus 180, which is just a negative 131. Like we said, this was a sum and a difference product. Same two terms, one's a sum, one's a difference. And it only works when there's square roots. If it was a higher root, third, fourth, or fifth root, it wouldn't have worked that neatly. But because they're square roots, they multiply out to make a rational number. Those numbers like that sum and difference product with square roots, is what is referred to as conjugates. And those conjugates become very important in our next steps of working with these radicals. For right now, that's all the time we have for the day. We're going to have our drill in a minute and a half here. So remember, homework 12C. Deals with our stuff today. After today, we got exactly 4 weeks left. So that's about 3 weeks of new material. Then we'll spend, depending on where we're at pace-wise, either we'll spend a day catching up or we'll spend a day reviewing before we do the final. Any questions? Okay, you guys have a great Easter.